This is the Riemann zeta function, worth $1 million. It can tell us where the prime numbers are once solved. It equals 0 at every negative even integer, -2, -4, etc. But it also equals 0 for seemingly random inputs with real part 1/2. But why care? The prime number theorem states that x over ln x approximates the number of primes before x. Plugging in Riemann's zeros makes it even closer. So we can find out where the primes are, but we need Riemann's zeros too. So what's so complicated about this? Well, we want the zeros. Trivial ones at negative even integers, and non-trivial as some complex numbers with real part 1/2. But we can't even plug these numbers in. We need a new function. This is that function. It works for every value less than 0. We got it through analytic continuation, which just extends the domain in such a way that it has a derivative everywhere, which just means it can be represented by simple polynomials. Analytically continuing the function is a lengthy process. By all means, pause and look through it, but it's not too important to know. So this is our equation. Doing it out, if we plug in -1 for s, it simplifies down to 1/2 times 1 over pi squared times -1 times pi squared over 6. Doing the math out, we get -1/12. Riemann's hypothesis says that non-trivial zeros have a real part 1/2, so this function doesn't work either. For 0 is less than s, we have this function. Once we have all three equations, we can start doing complex inputs. Think of imaginary numbers in terms of x and y. 1 plus 1i is the same as 1 comma 1. Graph cosine x plus I sine x. It's a circle. E to the ix is the exact same thing. Rotating pi, we get -1, which is how we got Euler's identity. For 3 to the I, we just take e to the I ln 3. For complex exponents, we just do this. With complex inputs, we can find non-trivial zeros, the first one being at 1/2 plus 14.1347. Riemann's hypothesis says that all non-trivial zeros have real part 1/2. So there are two ways of getting that $1 million. You can A, find a zero that isn't trivial or non-trivial, or you can B, prove that every non-trivial zero has to have real part 1/2. Do that, and you go down in history.